Hello, today we are going to be going over partial fraction decomposition. Partial fraction decomposition is used to break down fractions into simpler components. It is often used in integral calculus to construct simpler integration problems. The steps are as follows. First, we will factor the denominator of our fraction. Then we will write the fraction in partial fraction decomposition form. We will go over the different forms on the next slide. Then we will reduce the fraction, getting rid of the denominator using a common factor. We will then solve for constants and substitute those constants back in. Before we get started, there are a few rules to keep in mind. First, we need to ensure our fraction is proper. This means the degree on the bottom is higher than the degree on the top. You can see an example of this over to the right, in which the degree on the bottom is 3 and the degree on the top is 0. So this fraction is in proper form. If our fraction is not proper, we must do polynomial long division to get into a proper form. Next, we must identify what partial fraction form to use. We break up fractions into terms being added together, with constants represented by a, b, c, etc. on the top, and the factored numbers on the bottom. To the right are a few examples where the denominator has already been factored. Let's look at the first example. In this problem, there is one term in the denominator being taken to the degree of 3. We split this up into 3 terms, where on the numerators we have a, b, and c, and in the denominators we have our x minus 1 term being taken to increasingly higher degrees. So we have x minus 1 to the first power, x minus 1 to the second power, and x minus 1 to the third power. It's important to remember that our final term needs to have a degree that matches the degree of our original term here. Another rule to keep in mind is if we have a term with an x squared in it on our denominator. This is represented in our numerator by ax plus b. So in this example, our term x squared plus 4 is going to be broken up into ax plus b over x squared plus 4. And our x minus 1 term is being taken to the power of 1. So we can represent that as c over x minus 1. We can put these two rules together, like in our third example here, where we have an x squared in our numerator and our denominator, and it is also being taken to the power of 2. So we represent this by our ax plus b and cx plus d on our numerator. And then we also can see that our x squared plus 3x plus 4 term is being taken to the power of 1 here and taken to the power of 2 here, in which this 2 matches our original degree of 2. So let's apply these rules. We have an example here of 3x plus 11 over x squared minus x minus 6. So our first step is to factor the denominator. This can be done through the quadratic method or any other means. So we have two factored terms here, an x minus 3 and x plus 2. Next, we are going to write in partial fraction form. Our x minus 3 and x plus 2 have no x squareds in them, and they are both taken to the power of 1. So using our rules, we can write this as a over x minus 3 plus b over x plus 2. The next step is to reduce this fraction. We do this by finding a common denominator, which will always be the denominator of our original function equation here. In this case, we are going to multiply our a over x minus 3 by x plus 2 over x plus 2, and our b over x plus 2 by x minus 3 over x minus 3. This way, all of our terms have the exact same denominator, and we're able to add them together like we do in this step here. Now we are looking to get rid of that denominator, and we can do that by multiplying both sides by our denominator, so by that x minus 3, x plus 2 term. And when we multiply both sides by this term, they actually cancel out. We kind of cancel these out and cancel those out, and we're left with this one equation here. This 3x plus 11 equals a x plus 2 quantity plus b times the x minus 3 quantity. So step 4 is solve. And the way that I like to do this is I like to group our equation and then match our coefficients. So here I've just foiled out our equation. We have ax plus 2a, just foiling these out, plus bx minus 3b. And here I was grouping them. So we want to make sure that our terms for our x's stay together and our terms without our x's stay together. And then we're able to match them. In order for these two equations to be equal, our a plus b must be equal to 3. That's represented over here. The same applies for our 2a minus 3b. It must be equal to 11 for these two equations to be equal. So we have that over here. Now we have a system of equations in which we have 2 equations and 2 unknowns. So we should be able to solve for this. And when you do solve it, you get b equals -1, and a equals 4. Now we're able to substitute these into our original equation. So here we have 3x plus 11 over x squared minus x minus 6 equals 4 over x minus 3 minus 1 over x plus 2, where our b term is seen here in our -1 and our a term is seen here in our 4. We're matching our original form as seen up here. So that's how you do partial fraction decomposition. And this is an equation that is much easier to take the integral of, which is our main point in this process. So let's go over the steps real quick. First, we are going to factor the denominator, then we are going to write in partial fraction decomposition form. We are going to reduce through a common factor, we are going to solve for constants, and then we are going to substitute constants back in. If you're looking for more sources in order to learn more about partial fraction decomposition, feel free to look at any of the links here. So, thank you.